Hello, so today we are going to do this problem called minimum replacements to sort array, which is part of this week's contest. So the problem says we get an array of integers, and in one operation we can replace any element with any two elements that sum to that number. So for example, here with this array 5, 6, 7, in one operation we can replace the number at position 1, which is 6, with 2 and 4, because 4 plus 2 equal to 6, and replace that element. So now instead of 6 we have 5, 2, 4, 7, right? And the goal of this problem is to return the minimum number of operation to make the array sorted in non-decreasing order. So basically the minimum number of operation to make the array sorted in increasing order, right? So if we take a look at this example here with 3, 9, 3, clearly because of 9 it's not sorted, right? So the easiest way to make it sorted is to first break 9 into 3 and 6, and then to break 6 into 2 3s, and so we end up with 3 3s, and that will make the array sorted because all of them are equal. So here increasing or equal, right? This is already sorted, so we return 0. There is no operation. So one thing we can notice here is that the length is 10 to the power of 5, right? So definitely an oven squared solution won't work here. So yeah, let's see how can we solve it. Okay, so let's see how we can solve it. So the first thing to think about here is we want to always break an element into a smaller parts. We never want to make it larger, because essentially what the problem says is, remember, we need to break it into two elements that sum up to the number. So for example, for 9 here, we break it to 3 and 6, right? So that's the first thing. We only make the numbers smaller. And so if we do that, then let's say we have a set of numbers, maybe 8, 7, 6, 5, 2, right? If we go the usual way we iterate from left to right, then, well, we will find 8, there is nothing to the left of it, so we are not worried. But 7 is smaller, right? So that means we need to break 8 so that this is in order. So let's say we break 8 into something, maybe, I don't know, just something random like 3, 4, right? Now when we go to 6 here, again, 6 is smaller, so we need to break 7, right? But the problem is that whatever we break 7 with, that needs to also be smaller than whatever came before. And so we'll need to, if let's say here we do like maybe 2, 5, right? Because there is 2 here, this is no longer valid, so we'll need to break this again. So if we do it from left to right, that means for each number we will need to repeat the process for all of those to the left every time, which will end up to be at least an oven squared. This is without even mentioning the how we are going to break the elements. So breaking from left to right, that's not going to work, which means let's try from right to left, right? So if we do it from right to left, 8, 7, 6, 5, 2, then that's easier, because once we break 2, we need whatever we break it into to be smaller than 2. So let's say we break it into maybe 1, 2, 2, right? Then 6 needs to be smaller than these, but once we break it into elements smaller than these, by definition they will be smaller than this, because we made sure this is smaller than it. And so we only need to break so that it's smaller than the one before it, right? And we do that each time. So at the end it ends up being oven, right? So from right to left, that's what we need to do. So that's our first observation, is right to left. Now what about now, how do we break the number? How do we decide that we break it into this or 3, 4, like I said here? How do we decide? So the first thing we want to do is we want to make sure we want to do this in a greedy way, where basically we want to try to break the number into as large numbers as possible, because that means the numbers to the left will have a chance to be maybe if the number to be not broken, so we don't need to break it. What do I mean by that? So let's say we have a set of numbers here to the left, and then we have our number, and then we have 9 here, right? So if, let's say here we have 10, right? We want to break 10 into as large numbers as possible, so that, let's say if we break it into 5 and 5, that's better than breaking it into 4, 3, 7, 3, right? Because if we break it into this, and let's say we have 5 here, for this case, we don't need to do any operation, right? Because 0, it's already equal. But for this case, we need to do one operation to break 5 maybe into 4 and 1, for example, or 2 and 2, or 2 and 3. Because if we don't, then the condition is not valid of increasing. And so we are better off having a larger value, because that would give us a chance to not need to do one more operation, right? So that's the main idea here, to minimize, because our goal at the end of the day here is to give the minimum number of operations. So to be able to minimize the number of operations, we need to break the element into the element that needs to be broken, of course, because it's not respecting the increasing order, into as large elements as possible, larger elements, numbers as possible. Okay, so that's what the first observation. And the other thing is, of course, since we want it to be increasing, right, we know that the number, right, that we break x into, so we break x into maybe x1 and xn or xk, let's say k numbers, right? We need all of them to be smaller than or equal. So this x would be maybe a of I. A is the numbers array. This is ai plus 1, or let's call it just previous, right? So we need all of them the elements that we break it into to be smaller than or equal to prev, to maintain the sorted order of the array, right? So that's another observation to think about. Okay, so now what does this gives us something to decide how do we break it, right? So one thing to note is that if you have one k here, which is the number of elements we break the array into, k needs to be between, so we want, let's say the number here is a of I, or x, let's call it x, right? So let's call this number x, right? So at most we can do x, right? Because that's 1 plus 1, x times, right? So it's between 1 and x. 1 is not breaking it at all. One thing we can note is that it's possible to represent x as the sum of these k numbers such that they all differ by at most 1, right? Why? So basically we can break this into break x into numbers such that they differ by at most 1. So let's take a look at why, right? So if we have x here modulo previous value equal to 0, which means basically it's divisible, then what we can do is just divide x so that it's we have k be x divided by prev, right? An example, so let's say x is equal to 9 and the previous element is equal to 3. So this is the case here with this array. So if we do 9, so this is k. Sorry, this is prev here, that's what I meant. So this is prev. So 9 divided by prev, that's equal to 3. We can break 9 into just 3 elements, 3, first 3, 6, and then 3, 3, right? And this will be this will allow us to have only k equal to 3. So in the case x modulo prev is equal to 0, we can just break the number into k such that k is equal to x divided by prev. In the case where x modulo prev is not equal to 0, equal to 1, these are the only possible 2 cases. Then in that case, well, we can't do the equal, breaking them into equal numbers to the previous element. but we can do it such that they differ by at most 1. So how do we do that? Well, we can just have our count be equal to x modulo previous plus 1. Let's take an example. So if x is equal to 10 and the prev is equal to 3, we can't do this here because then we'd have 1. But 1 is smaller. We want these numbers to be as large as possible. So what we can do instead is maybe have, let's say, we can have either 3 or 2 to be smaller, to have the difference be not larger than 1. So we can do maybe 2, 3, so that gives us 5, right? And then do another 2, 3, right? That gives us 5 as well. And this would be k equal to 4, which is exactly, so this is divided actually, which is exactly this because that's 3 plus 1. Okay. We would have to have a fourth number, right? Because prev is equal to 3, and you can't divide 10 by 3. 10 divided by 3 is you have to keep it below or equal to 3, right? So the best we can do is something like this, right? Because at the same time we maximize the element. Yeah, so what can we reduce this then into a formula? Well, it's either if it's equal to modulo equal to 0, then if it's modulo equal to 0, then it's divided, otherwise it's plus 1. So we could either do this condition with if and else, or even easier, this is actually just the ceiling of x divided by prev, right? Because if you do 10 divided by 3, that would be like, I think 3.5 or something like that. 3.3 or something. And then the ceiling of that is just 4, which is what we want here. So this would be the count of the numbers that we split x to. So how many operations do we need with this count? So we need count minus 1 operations, which means that's what we are going to increase our operations by. Why is that? So let's say we have x, and which let's take the case of 9. We had to split it to 3, 6, and then 3, 3. So we had to split it into 2 3s here. How many operations we need to do this? So the first operation to get 6, and then the second operation to break 6. So if we generalize this, it's always count minus 1 or k minus 1 here. Okay. Okay, so we know k. We know what we need for our k value here, which is the number of elements we break it into. So we actually don't need to like physically break it, right? Because we only need the number of operations. So we increment. But we do need, so once we need to identify now what's the previous element for the next iteration, right? So let's say we did it for 5. We broke 5 into maybe 2 to 1. In this case, that's the best solution. We need to we need a way to have the previous operation, the next operation considering prev to be equal to 1, because anything here needs to be smaller or equal to 1. So what's the value, the smaller value here? Well, that's just actually the x value, which is a of I, divided by k, the count, right? Because we are going to divide x into k elements, right? So the smaller one would be this, x divided by k, the integer value there. So this would be our new prev value. And that's pretty much it. So let's summarize here a little bit. So we know that we'll traverse from right to left. That's our first thing. The second thing is that since we want to break elements into as large as possible elements, we can know exactly how many elements we need to break it into by just using this formula. And from that formula, we can deduct how many operations we need, which is k minus 1. And then for the next iteration, we can do prev x equal to the element at position I, which is x divided by k, right? Now, one more thing is that we only need to break the elements if it's bigger than the elements to its right? If it's smaller or equal, we don't need to do anything. We just need to set prev to be equal to that value, so that for the next iteration, we take it as the previous value, right? And yeah, that's pretty much it for this problem. So with these observations and ideas, let's write the code and make sure it passes. Okay, so let's write down the implementation here. So what we need is, so let's first just have this to be the length of the numbers, or since in the explanation we named it A, let's just name it A here. So we need the overall number of operations. That's what we are going to return. And then we need to keep track of the previous. So for, let's say, a set of numbers like 5, 6 maybe, right? 4, right? We don't need to check for this element because there is nothing to its right that it needs to be smaller than. So we can take that as our previous value, which is the last element. And for our while loop, for our iteration, we need to go from right to left. And as I said, we don't need to take the last element since there is nothing to its right. So we need to start from the second to last, so the one just before the last. And we need to go right to left, so we need to keep going down until we reach 0, which is the first element 1 here. Okay, so that's our loop. Now, if the element, we only care about breaking the elements if it's bigger than the previous element, than the element to its right. So this is where we break the element. Otherwise, we don't need to break the element, but we need to set prev to a of I, so that, let's say, I is equal to n minus 2. When we go to n minus 3, the previous element we will be considering is 6. So that, let's say this is 9. If we compare it, we will know 9 is bigger, and we need to break 9 is bigger than 6, right? So we need to set prev here once we move, right? And now how do we break the element? We said that now with the observations that we did, we know that the count, or what we named k, let's call it k here, it's actually just the ceiling of x, which is a of I, divided by the previous element, right? Because it needs to be smaller or equal to that element, but we want them to be as large as possible. The overall count is going to be basically depending on whether modulo equal to 0, whether it's divisible. If it's divisible, then it's just a of I divided by prev. If it's not divisible, then a of I divided by prev plus 1. So that's why we need the ceiling here. And now we need to increment the number of operations by k plus 1, because k is the count of elements. So k, count of elements to break a of I into, which means the number of operations we need to break x, let's say, into 3 elements is 2 operations. So count minus 1, or k minus 1 as I named it here. And now what should be our prev value? Prev value should be the smaller of all the elements we're breaking it into. So let's say if we had broken a number into 3, 3, we need prev to be 2, because we are in ascending order technically, right? We want the array to be in ascending order. So prev here needs to be the smaller element, and since we said the difference is at most 1, the smaller element is divided by, k. So this will give us the smallest element in the set of elements we broke a of I into, and that's what would be the previous value. And that's pretty much it. So if we run this, yeah, I forgot to delete this. Let's use more examples. Let's submit. Okay, so that passes test cases. Now, in terms of time complexity, this we are doing one loop, so it's O of n time. And then in terms of space, we are only using constant space here with pref and operations, so it's O of one space. Yeah, so that's pretty much it for this problem. Thanks for watching. Please like and subscribe, and see you on the next one. Bye.